Hi everybody, I'm AG, and before we start to solve questions, let's review what we've learned on Unit 3. A function is a relation that obtains an output from an input value, creating the function image that is generally associated with its graph. Also, a function can serve as a composite relation with that combined expression. If all function domain elements have different images, it is said that it's a one-to-one function. If all elements in the domain have image, it's a one-to function. Finally, if a function has these two features, can be reversible. Any rearrange of elements in a reversible function is a permutation. And we know that can exist as much as n factorial of them. Also, we discussed multiple mathematical functions. Floor returns the number rounded to the less integer. Ceiling returns the number rounded to the greater integer. The integer returns the number without its fractional part. The absolute value of a number returns a positive version of the number. The module function performs a defined operation between two numbers. The exponential function raises the first number to the second, and logarithmic finds the number that the first one must be raised to obtain the second. There are some functions who especially behave like the sequences, that given an n-term expression expands obtaining a series of elements. The summations define a sum of terms from the start point to the end. The recursively defined functions calls to themselves. The purpose of all this content is to introduce the idea of algorithm and its time complexity according to an hypothetical worst and average case. All this expressed throughout the big O notation. First question, we have these ordered pairs and we must give the green light to be a valid function pairs. We want to point out that the important element here is the first pair term. By example, in this relation, a function never will return different outputs from the same input, so this is false. In this one, this cannot serve as the domain because it doesn't contain the number 2, false again. This could be a valid function despite the duplicates. While being an x set term, we don't care about the second pair term. Question 2. We must sketch the graph for these two functions. Find the axis intersections and evaluate in a smart way. The first one is a polynomial function. Let's find the points where the line intersects the x-axis. Replace y by 0, and to solve this expression rely on the Ruffini coefficients method. We found that the line intersects on x equals to 3, x equals to -1 and 1. To find the y intersection, we replace x by 0, obtaining 3. So, having this data, start to draw the line, giving some points before and after there is the first image. In the second function, when we make y equal to 0, have the x variable in the logarithmic expression. So a good way to clear the x is to apply a base 2 exponent, producing a division by the exponential properties. In that way we found that the line intersects x in 8. For the y intersection, we make x equal to 0, and here we have an inconsistency. There is not a number to give a 0, so there is not y intersection as well. So, the line intersects x on 8 and never will intersect the y-axis. It must be anywhere in this region. We are going to give some values before and after the intersection, and there is the second function image. Question 3. Having these f and g functions, find the composite pairs elements. This is just the composite relations extended to the idea of a function. In other words, find a way to go from A to C. Question 4. Having these two functions, f and g, find an expression to evaluate the composite function. Here just replace the independent variable for the inner function expression, and then the composite function can be evaluated. Question 5. Given these functions f, g, and h, find a way to identify who is one-to-one, onto, or reversible. First, identify the sets involved to see things more clearly. After that, we organize an arrow diagram, and finally building a matrix is maybe the fastest way to answer. F and H are one-to, not one-to-one functions. G is one-to-one, not one-to function. No one matches the two conditions here, no reversible functions. Question 6. Evaluate each of these outputs. Floor, the less integer than minus 5.3 is minus 6. Ceiling, the greater integer than 1.3 is 2. 120 the factorial of 5. Floor, the less integer than 3.3 is 3. The square root of 10 is 3.162. Close but false. 2 raised by 3 is 8. 2 raised by 0.5 is equivalent to find its square root. The number to raise 2 and obtain 4 is 2. The less integer than minus 1.2 is minus 2. The greater integer than minus 0.75 is 0. The factorial of 3 is 6. The less integer than p is 3. The square root of 10c is 3.162 times the square root of c. 1 raised by 0 is 1. Now, 3 meters raised to the square is 9 square meters, not 9 meters. And finally, 3 raised to 0 is 1. Question 7. Find each module remainder output. Always solve the inner expressions first. The module of minus 2 and 0, this is an undetermined number. As we said before, we are working on the real numbers set. The module of 6 and 3 is 0. The module of 4 and 16 is 4. For m equals to 1, the module is 1. The module of 0 and 3 is 0. The module of 40 and 25 is 15. And the module of 23 and 24 is 23. Now, g is a function that takes two inputs, a and b. If b is greater than a, the function will output 0, and this is called the base value for stop g. While a is greater or equal than b, the function will be referring to itself, subtracting the b value from a like this. So, let's see what's going to happen here with these two pairs as function arguments. For 2 and 3, b is greater than a. Yes, so g returns 0 and stop, there is nothing to do. But if we enter 5 and 1, a is greater than b. In this way, g will be referring to itself, subtracting the b value in each iteration from a like this. There, g has reached the base value to returns 0 and stops. The last question, an algorithm involving a binary search whose big O notation is widely known, takes 4.6 time units to do its task. How many elements were input there? With its time complexity expression, it's quite easy to equal the expression to the time required and apply base 2 exponent to clear the end value. There we have the approximately 24 elements producing this behavior. And this is how we end Unit 3. By the way, if you want to learn for a more advanced test exercises, a link in the video description will be available. Thank you very much for watching our video and see you on the next unit.